Hello everybody. Today we'll be having a lecture on block cipher encryption modes. This is an add-on lecture to the previous one, which was on symmetric encryption schemes. If you haven't watched that video prior to this one, we highly encourage you to do so. So, we'll be specifically covering block cipher encryption modes. And there are a variety of encryption modes that exist. However, we'll primarily be focusing on the general use ones. One of the first ones is the electronic code book, ECB. Then there's cipher block chaining, counter mode, output feedback mode, and cipher feedback mode. In these lectures, we'll also talk about one authenticated encryption mode known as Galois counter mode. However, it's important to note that we do not cover all of the encryption modes that exist in the world. Some encryption modes are standardized by different authorities, and we cannot cover all of them that exist. As such, we primarily focus on the general use ones, and at least give you an idea of how authenticated encryption works. Now, before we get into the technical details of each encryption mode, let's talk about the notation that we use throughout this lecture. So, as we know, K will stand for symmetric encryption key. In this case, we keep this key secret, and only the communicating parties know of this key. Then there will be the initialization vector, or I'll sometimes refer to it as the nonce. In this case, the initialization vector is a public value that can be known to anybody without compromising security. Then, as covered in the previous lecture, there are plaintext blocks, namely, we split our plaintext into equal-sized blocks for the encryption circuit to work. The encryption circuit will produce ciphertext blocks, which will be denoted as C up to Cn. Then, for some operations, we'll need the exclusive OR XOR operation. To put it shortly, here we provide the truth table to how an exclusive OR operation works, as to give you a small reminder of what it does. Then, to denote encryption, we use this notation of EK, where simply it's some sort of encryption with the key K. In other lectures, you may see this notated as E with the key K for some sort of plaintext Pn. Next, we'll also use counters. So in this case, a counter is a very simple function that starts off at 0 and gets iterated by 1 for each new counter that exists. So we'll denote counter n as a different counter and a different iteration from it, starting from 1 to plus infinity. And lastly, we'll use something known as a left shift register. This left shift register will push whatever input to the left by m positions or m bits. But we'll talk about that a bit later, and we'll give an example of how that works in a couple of slides. So, let's begin with talking about the cipher modes and technical details behind them. The first one we're going to talk about is the electronic code book, known as ECB with an abbreviation. So, it is the most simplistic and most straightforward encryption mode, and it only requires the plaintext and the key. So in this case, the plaintext is divided into separate plaintext blocks, and then each block is encrypted using the encryption circuit, which produces a corresponding ciphertext block. This continues for all the blocks until we have the full ciphertext built. However, there is a clear issue with the electronic code book, namely, the outcome of this cipher mode is always deterministic, as it has no probabilistic elements within it. And this creates a clear link between the plaintext and the ciphertext. This can be directly seen in what is known as the ECB tux. In this image, you can see the plaintext on the very left, and you can see that when encrypting with the ECB mode, the ciphertext ends up still retaining the overall form of the plaintext, leading to some privacy loss and a very clear privacy issue. And this is namely solved through the use of different encryption modes. And to basically solve this, we introduce a probabilistic element alongside the key, namely the initialization vector, or the nonce. As such, one of the examples of using a probabilistic method, a probabilistic element alongside the key, is the cipher block chaining mode. In this mode, we have the plaintext block as well as the initialization vector. These two elements are XORed together, and then the outcome of this XOR is encrypted using our encryption circuit. This produces our first ciphertext. As we don't want to reuse the same initialization vector, we end up using the same ciphertext that we produced in the previous block. So to encrypt the next plaintext block, we XOR the ciphertext block 1 as well as the plaintext block 2. This then continues on to the next encryption circuit, which produces the next ciphertext block, and this continues until we encrypt the entire plaintext. A different way of doing this is through the counter mode. In counter mode, we still use the initialization vector. In this case, it's usually called the nonce, the number we only use once. And this nonce, or initialization vector, sets a counter to that certain value. The counter is initialized at 0, then it gets set to the initialization vector, and then the encryption process begins. Namely, this initialization vector is encrypted with the encryption circuit, and this output is then XORed with the plaintext block to produce the ciphertext block. Then the counter is iterated by 1 to, so let's imagine the initialization vector was the number 15, so the counter will then iterate it to 16 and continue on from there, doing the exact same thing to produce the second ciphertext block. This continues for all the plaintext blocks that exist until we have the complete ciphertext. In output feedback mode, we also start with the initialization vector, but we forego all the counters and XORing, and we directly encrypt the initialization vector. Then this output is used to XOR the plaintext, XOR the plaintext block with this encrypted initialization vector to produce our first ciphertext block. Now, to actually provide the continuation of this, we actually use the output of the encryption circuit, namely, as the name implies, output feedback. We send that over to the next encryption circuit, which will then be XORed with the second plaintext block to produce the second ciphertext block. And this process continues until we finally end with the full ciphertext. The last cipher mode in the general use category that we'll cover is the cipher feedback mode, which works very similarly to the output feedback mode. In this encryption mode, we once again start with the initialization vector, which gets encrypted using our encryption circuit. Now, it's important to take note that the initialization vector is of n bits long, and after the encryption circuit, we produce a ciphertext that is also n bits long. However, we first select the first m bits of the ciphertext, and the remaining bits are discarded. Namely, n minus m bits are discarded, and m bits are selected. These m bits are then used to XOR with the plaintext block. The plaintext block is going to be the same length as the amount of bits that we selected initially, and this will create our ciphertext block, which is also m bits long. Now, these discarded bits end up getting sent to the left shift register, where they end up getting shifted by m positions, and the remaining ciphertext and the remaining output is padded with the ciphertext block C1 that we outputted previously. Then this output is once again encrypted, and the process continues to produce the second ciphertext block, as well as produce the remaining ciphertext blocks in the exact same principle. So to better understand how the left shift register works, let's have a quick example. So let's imagine our encryption circuit. It ends up producing a ciphertext of 9 bits. So these n bits are basically the output of the encryption circuit. We end up selecting the first 4 bits and discarding the remaining 5 bits. The bits that we selected end up going through the encryption process, namely the XOR operation, to produce the first ciphertext block. And now the remaining bits that we mentioned, the n minus m bits, look something like this. We have the first 4 bits, which are completely useless to us, they are empty, and then we have the remaining 5 bits, which have actual information in them. So we send over the ciphertext into the left shift register, which pushes the 5 bits to the left by m bits. Namely, in this case, it's going to push it to the left by 4 bits, removing those empty squares and leaving us with an output like this. However, to input it into the encryption circuit, we need something that is n bits long. So to do this, we simply want to pad our output. So in this case, we reuse the ciphertext block that we made previously and end up creating a new input that looks like this. So the first n minus m bits are on the left. These are the ones that we discarded previously. And then these m bits is the ciphertext that we produced with the selected bits. This in total creates n bits, which we can then pass off to the encryption circuit and continue this process from here. With that example, we end up covering all of the general use encryption modes that we set out to cover. Now we've arrived at authenticated encryption, and in this case we'll be talking about Galois counter mode. So Galois counter mode consists of encryption and authentication. First up, let's cover the encryption. As the name implies, it uses the same things we've talked about previously, namely the counter mode. So the process is the exact same, with one key difference. The initialization vector sets our counter, which is then encrypted with our encryption circuit. However, this encryption circuit does not continue anywhere for now. It'll become relevant later, but for now, we iterate on the counter and then start the process as we imagine it from the counter mode. So only after the first iteration, we start encrypting the plaintext blocks. This process continues until we encrypt all of the plaintext blocks into their respective ciphertext blocks. With this, we enter into authentication. So to understand authentication, we have to understand Galois fields. In this presentation, we're not going to be covering what are Galois fields, how we do operations on them. However, we have a link to a couple of videos that will help you understand what Galois fields and how to do operations on them. So we highly encourage you to watch those and then come back to this video if you have any questions. However, we will not require you to know or understand Galois fields in any of our exercise works or in any of the coursework. This is purely for your own knowledge and for your own information. So, with that out of the way, we can continue on with how the authentication works of the Galois counter mode. So first, we have some data that we want to authenticate. Let's call it auth data, or simply A. This data is multiplied in a Galois field of size h, and then the output of that multiplication is used in an XOR operation with the first ciphertext block. Then we once again perform the same Galois multiplication and continue that through all the blocks that we have of the ciphertext. Eventually, we reach the very end, namely ciphertext block n, and we XOR it, and once again multiply it in the Galois field. Then, as the final steps of this operation, then we find out the length of A, which is the length of the data that we inputted, as well as the length of C, namely how many ciphertext blocks we need. From that, we XOR the latest multiplication with this new data, multiply it again in the Galois field, and then XOR it with the very first encryption of the very first counter we did. And this ends up producing our authentication tag. We have not exactly covered how authentication tag is or what message authentication codes are as of now. However, this is a way of doing it with an encryption mode. So we've covered 5 general use encryption modes and 1 authenticated encryption mode. And one thing that is important to think about when choosing your encryption mode is the parameters you will need for both encryption and decryption. So in this table, you can see a quick summary of what parameters you'll need to perform encryption and what parameters you'll need for decryption. So in this case, in all the encryption modes, you'll naturally need the key and the plaintext. And for decryption, naturally, you'll need the key and the ciphertext. However, modes such as CBC, CTR, OFB, CFB, and GCM, you will also need the initialization vector. As mentioned previously, this initialization vector can be made publicly. It's usually appended to the start of the ciphertext, however, it can be transmitted in any other way. And specifically in GCM, for encryption, you will also need the data that you want to authenticate, and for decryption, you will also need to provide the tag. If you do not provide this tag, or if the tag is invalid, then the encryption will fail and will not be able to decrypt the ciphertext in most cases. So, now that we've covered all of the cipher modes, you may have a question, namely, what to use. Which cipher mode is the right one to use? However, there is not a concrete answer of you should use this one or you should use that one. Everything is very dependent on the situation, and you have to deeply think about various questions and answer those questions to understand which cipher mode you actually want to use. Some of the questions that you want to keep in mind is, do you need parallelization? Do you need your encryption or decryption, or both, to be parallelizable? In this case, both encryption and decryption is parallelizable on the counter mode, as well as the electronic codebook mode. However, others do not allow parallelization at all, or only allow parallelization of decryption. Another question is, are transmission errors going to be common? In the case that you're using, let's say, UDP to transfer information from one point to another instead of TCP, you may encounter transmission errors. In modes such as cipher block chaining or cipher feedback mode, a single transmission error can cause all subsequent blocks to be undecipherable, undecryptable. So in this case, maybe using a different mode might be the more correct way of using it. A single block being undecipherable is going to be better than the entire ciphertext being undecipherable. Then you may want to ask, what kind of security do you need? Do you only need ECB? Or maybe you need more strict security, such as the ones provided in CBC or OFB? And also, do you mind the use of padding? Padding can be sometimes problematic in security by having the same block being at the very end. So in this case, you have to answer, do you mind using padding in your ciphertext? Namely, in the case of ECB or CBC, you have to use padding if your plaintext is not long enough. And then other frequent questions that you may want to ask is, what is the use case specifically that you want to use? Is it just communication encryption? Then maybe one of the general use schemes is enough for you. Maybe you want to do disk encryption. In this case, maybe none of these modes actually work for you, and you may want to use something different. Something we haven't covered is XOR encrypts XOR, or XOR encrypts XOR with ciphertext stealing, known as XTS. Those modes are more commonly used for disk encryption than all the ones that we've covered previously. Or maybe you need specifically authenticated encryption when you aren't sure who is going to be deciphering your ciphertext and you want to be extra sure that it hasn't been modified in any single way. Then maybe using modes such as GCM is the way to go here. We cannot immediately answer you which ciphertext mode is the correct one to use. Each use case will have its own merits and its own downfalls. So at that, think which cipher mode you want to use and what fits your needs the most. With that, we shall conclude this lecture, and we'll see you next time on the next lecture on asymmetric encryption.